All right, so welcome everybody to today's colloquium. It's really my pleasure to introduce Professor Malena Rice. Malena is an assistant professor at Yale. She first finished her PhD at Yale in 2022. Then she won the 51 Pegasi B postdoctoral fellow. She brought it at MIT. She already has a number of achievements, so let me just mention a few. She was listed in 2023 in the Forbes 30 under 30. Then also in 2023, she was mentioned as Rising Talent by the Women's Forum for the Economy and Society. And then in 2024, she was selected as a Scialog Fellow. So I'm really excited to hear her talk about the orbital architecture of planetary systems. So take it away, Malena.
Thank you, Ilaria. Thank you, everyone, for joining. So today we'll be talking about a couple of different ideas within my research program to understand the dynamical evolution of planetary systems by looking at the distribution of orbits that we see today. So I am interested in my program and aiming to unveil what it is that's actually sculpting this very broad diversity of exoplanet systems that has been observed, and placing that into this context of understanding what this means for our solar system in this broader context of the many, many planetary systems that we see that are very unlike the solar system. So I'll be talking about a range of topics related to that today. I wanted to start by just acknowledging my fantastic research group. So I started at Yale a couple of years ago, and the group has been growing, and I work with a really wonderful group of, these are the postdocs and graduate students that I've worked with over the past year, as well as quite a few fantastic undergraduates. And so a lot of the work that I'll be talking about today has been led by or heavily contributed to by this fantastic group. So if we look at a very, very stripped down version of the solar system, it looks something like this. We have 8 orbits. This is actually kind of more than what we know for a lot of exoplanet systems, in that we know the orbital eccentricities of the planets in the solar system quite well, very precisely. We know how many planets there are in the solar system, with a little asterisk if you believe in Planet 9. And we sort of know what lies in addition in between these orbits. There's actually a lot more that we know about the solar system than what's shown in this picture, and yet this is kind of in ways sort of more than what we know about a lot of planetary systems beyond our own. If we take this and sort of flip it around, we can see that the solar system is reasonably well described by coplanar orbits. It's not perfectly, there are small mutual inclinations between the orbits of the planets, but they are fairly well approximated by a disk that is where all of the orbits of the planets lie. And that disk is a little bit tilted relative to the way that our host star spins, our sun, by about 7 degrees. And this is also something that we're able to study for exoplanet systems. They're not always so close to this nice alignment as what we see in the solar system. And so this is what I'll talk about in the first part of this talk, is sort of what are the physical mechanisms that are tilting planetary systems beyond our own, and what can that teach us about the evolution of different kinds of planetary systems. In the second part of my talk, I'll go over kind of this idea that oftentimes we're thinking about planetary systems sort of like this, but often, in many cases, around half of solar type stars, and even more for the larger stars, our stars often come with companions, and so they have bound stellar companions that are also going to shape the way that those systems are evolving over long time scales. So in the second part of my talk, I'll discuss how these stellar companions are influencing our planetary system's evolution as well. And if I get to it, I'll have a bonus third part, but I want to make sure I don't keep people here too long. So we'll see how far I get and see if I can get to a bit more on the solar system as well, and some of the work I've been doing there. All right, so I want to start with part 1, which is what physical mechanisms are tilting planetary systems and what we know about this beyond our own solar system. So I mentioned this is kind of a simplified schematic, again, of our solar system. We've got this small, roughly 7-degree tilts between the net orbital angular momentum vector of the solar system planets and the spin axis of the sun. But if we look at hot Jupiter systems, then we see that many of them are on very heavily spin orbit misaligned orbits. And so We have some that are kind of more similar to the solar system, where they're consistent with being perfectly aligned with the way that the star spins. That's kind of what we would expect from a primordial system where everything is spinning together. You end up just forming planets that are orbiting in the same direction that your host star is spinning. But many hot Jupiters have been found on these kind of wacky sideways backwards orbits that are quite unlike what we see in the solar system. And so this gives us an opportunity to try to disentangle what is it that's actually producing these systems that are very, very different from our solar system, and what is causing something more like our own solar system versus a hot Jupiter system. So if you see a tilted planetary system, there are a lot of ways that you could produce such a system. So this broadly falls into two categories, and there are many sub-mechanisms within each of these categories where you could either say, all right, well, if you tilt your protoplanetary disk somehow, there are lots of ways that you might be able to do that, generally from some sort of external force, but they don't always require another star. Then you could form a planet that is on a misaligned orbit and a misaligned disk. You could also misalign your planets after you form your planets in the first place. So you could say, all right, maybe we form our planets in a disk that is it has a very small tilt, maybe more similar to the solar system, or is perfectly aligned, and then something else can put your planet on this weird sideways backwards orbit, like what we see for many hot Jupiters today. So this is sort of generally how you can tilt a planetary system, but you can also map this to these arguments for how hot Jupiters form, where you could say, all right, well, what we end up observing at the end is just a planet that is on a spin orbit misaligned orientation. But there are a couple ways that you could get there, where you could say either you tilt your disk, and this would correspond to potentially in situ or disk migration, which are two ways you can get a hot Jupiter: either somehow form it in place, a very, very massive planet very close to the star. Could be tricky to form in situ, but one could argue maybe in certain cases that could be possible. Or you could say, well, maybe after the fact, you could undergo this high eccentricity migration mechanism where you launch your hot Jupiter onto this really elongated orbit, this really eccentric orbit. When it is reaching this periastron approach very close to the star, it is tidally dissipating energy much more efficiently, and you're able to circularize your hot Jupiter over short time scales. So this sort of maps onto these ideas for how you get spin-orbit misalignment, but you can also figure out what that means for different hot Jupiter channels. In addition to hot Jupiters, I wanted to mention there's a lot more that you can get from stellar obliquities. So this is a slide that I made a couple of years ago with just a couple of things that I wanted to start pursuing in more detail, why it is that we want to get these measurements in the first place, and what you can actually start to answer. So some of these questions about, are disks commonly misaligned? Is there some relationship between age and this alignment? And what would that tell you about when you're actually getting these misalignments? As well as several of these other questions that are here on the right. And specifically, how do hot versus warm Jupiters form is going to be something that I talk about a lot in this talk. And so there's a lot of progress that I'd say we've made on quite a few of these questions. And I say we generally as a field, there have been a lot of these observations taken to actually get these spin orbit measurements recently. The way that we can actually get these observations is kind of remarkable that we are able to learn about this angle for exoplanet systems. But there's a niche where this is actually possible, where if you have a planet that is transiting over its host star, then it will block out preferentially one side or the other of your spinning stellar flux. And so if you block out some of the blue side of your flux, it will look preferentially as if your spectrum is a little bit redder, or vice versa if you block out some of the redder light, such that if you just pull out a radial velocity from your spectrum, it'll look like it's sort of slightly redder or slightly bluer, or you can actually measure the line profiles and see that distortion as well directly. So this is called the Rossiter-McLaughlin effect. It's been used for over a century at this point to also look at binary star systems. And more recently, starting with Kalos et al. 2000, has also been applied to exoplanet systems. And at this point, we have over 200 of these planetary systems that actually have these spin orbit measurements. This is something that is easiest to do for deep transits. And so we will focus on giant planets right now, but I wanted to mention that it's really a frontier to start pushing to smaller and smaller planets and actually figure out how those systems are oriented in 3D as well as the more giant So just to kind of give you a sense for what these signals look like, if they're symmetric, you end up with this little warp if your planet's going the same way your host star is spinning, and you have sort of the blue side and the red side are covered up for the same amount of time, versus if you have an asymmetric, a misaligned orbit, then you end up with an asymmetric signal. That's here. So there was a kind of seminal finding in 2010 that hot Jupiters around hot stars are more often misaligned than those around cool stars. So as more of these observations were taken, it started to be noticed that many hot Jupiters were on these kind of crazy orbits, and that there appeared to be a relationship with the stellar type. So if you were looking at massive hot stars, then you end up with a lot of misaligned hot Jupiters, and not so much if you look at the lower mass cool stars. So just to kind of guide your eye here, at the bottom here, these are aligned orbits, or these are consistent with being aligned, which is saying that planets are orbiting the same way the host star is spinning. So lambda is the projected obliquity. It'll come up in a bunch of figures. And if it's small, then that means that everything's sort of oriented, spinning in the same direction. 90 degrees you can think of as a proxy for a polar orbit, and 180 degrees you can think of as a proxy for a retrograde orbit. And I say proxy and not exact because these are 2D projected angles. So we don't actually know the exact orientation without this third line of sight degree of freedom. But we know that these systems are heavily misaligned, and we just can't say exactly how misaligned they are unless we get that third angle. So what was found in this 2010 paper, again, is hot Jupiters kind of to the right of this line are misaligned. The ones to the left tend to be aligned. And the argument here was that this line is somewhere around the Kraft break, where you start having stars that have a convective envelope below that line and a radiative envelope above that line. And so perhaps the systems that are aligned here could have actually started with the same distribution as those around the hotter stars, and they were able to realign through tidal interactions with their host star, or rather the star was able to realign with the orbits of the planets over some reasonable short time scale. And so this was the argument that was put forward in this 2010 paper that was saying maybe this is the reason that we actually see this break that corresponds to the Kraft break, is where you start seeing this difference of alignment versus misalignment. So if we fast forward 15 years later and get much, much more data, many, many more systems, this is, again, just looking at hot Jupiters, but we still continue to see that there are a lot of misalignments around hot stars and not so many around the cooler stars. And the line that we draw here is about that Kraft break location. So taking a step back and thinking, okay, what does this actually mean for how hot Jupiters form? If we return to this schematic here, on the left, there's no particular reason to believe that hot Jupiters in this particular framework would have ever reached more eccentric orbits. Whereas on the right, sort of by definition, if you are dynamically exciting your hot Jupiters to really high eccentricity orbits and then inspiraling them, they have to have a high eccentricity at some point. So now that we had much more of this data, and we were able to actually start parsing the sample more, we said, okay, well, let's just break this into bins of eccentricity and see if there's any relationship between eccentricity and sort of this misalignment that we're seeing to get a clearer picture of what's going on in the evolution of these systems as a population. So this was kind of a figure that we ended up making that is one way to visualize this, where we ended up seeing that hot Jupiters on eccentric orbits are fairly often spin orbit misaligned. And what we're seeing here is a cumulative sum of these lambda values, these spin orbit angles, for eccentric orbiting hot Jupiters. So that's these purple points. And so basically it's linear. There's no particular difference below or above the Kraft break in the typical lambda value that you're getting. Versus the circular orbits, we have way more hot Jupiters on circular orbits. So we just sampled random values from above and below the Kraft break. And you can see that there's this shallow increase that becomes much steeper above the Kraft break that corresponds to this difference at the Kraft break. So what I'm saying here is that the slope is not, it's not a shallow increase and then steeper at the Kraft break for the eccentric orbits, but you do see that for the circular orbits, for both all the full planet sample and the giant planet sample itself. Another way that you can visualize exactly the same data is by saying, okay, well, instead we're going to put all of our planets into 4 bins, and we'll say, look at just the eccentric orbits around hot stars, around cool stars, the E=0 orbits around hot stars and around cool stars, and just show what the distribution is of these spin orbit orientations. And we plot this on top of several mechanisms that are kind of the distributions of spin orbit orientations you would expect for starting points that are related to that are related to high eccentricity migration. So if you undergo, if you have numerical simulations that run planet-planet scattering, what is the spin orbit distribution that you tend to get from that? That's like the gray line that you see here, and the same for a couple of other mechanisms. And what we end up seeing is that all of these distributions overlap very nicely with those models that you'd expect for high E migration, except for this one in purple, which is the planets that are on circular orbits around cool stars, which are the ones that, if you believe in this sort of tidal realignment framework, are the ones that should be the most tidally evolved. So they're very close into their host star. They've perhaps reached the end point of circularizing as well as realigning. So really what we end up seeing from this figure is that this difference is significant only when you look at circular orbits. And maybe another way to visualize this is something that's been kind of claimed since 2010. And what we added was just this extra axis where we don't really see strong evidence for any difference at the Kraft break, except if you're looking at the hot Jupiters on these circular orbits. Okay, so what does that actually mean? It seems to hint towards this framework that's on the right, which is that we're seeing spin orbit misalignments and eccentricities perhaps of some sort of relationship. But we can do better than that. This is, I think, one line of evidence, but we need a couple of lines to really truly believe that high E migration is going to be dominant for our hot Jupiters. So something else that we can do to start addressing this question further is we can look at kind of the neighbors to hot Jupiters, that is the warm Jupiters. So these are very similar to hot Jupiters in many ways. They are often defined as this breakpoint at a period of 10 days or greater is often considered a warm Jupiter, or shorter than 10 days is often considered a hot Jupiter. I like to use A over R star space, which is the semi-major axis over your stellar radius, because this is more relevant for your tidal realignment timescales, just how close you are to the host star in terms of its stellar radii. And so warm Jupiters, although they're on just slightly wider orbits, tend to have many nearby planetary neighbors, and they're quite difficult to form through high E migration. So you can try to invoke having extra planets in the system that sort of shepherd your warm Jupiters in, but it's tricky to get this framework to work at scale for your warm Jupiters. But more importantly, actually, is just the fact that these warm Jupiters are on sufficiently wide orbits that they're actually quite difficult to tidally realign within the lifetime of the system. And so if you see an aligned warm Jupiter, then it probably started aligned, and you don't have to worry about all of these tidal models where the efficiency, your tidal Q, is not very well constrained. For the warm Jupiters, if you see an aligned system, then it would be quite difficult to align it over the course of its lifetime, so it probably started aligned. Okay, so this sort of led to the production of this survey that I began as a graduate student and have been continuing to co-lead with Song-Hu Wang, who's an assistant professor at Indiana University. And I also wanted to mention Shan-Yu Wang, a postdoc working with Song-Hu at Indiana University, has been really pivotal in this effort. And this really originated from me making like way too many plots, like hundreds of plots as a grad student, and noticing this really strange sort of, I wouldn't even call this a trend at this point, but just what seemed like a weird anomaly to me at the time, which was that if you break your systems into your cool stars and your hot stars, I mentioned again, for hot star systems, we see lots of misalignments, cool stars we don't. But if you look at wide orbits, we were seeing that the hot star systems, there were just none that were misaligned. I thought that was really strange and kind of the opposite of what I would have expected. So we said, okay, we'll go out and we'll figure out if that's real and just get more measurements to actually see if this is statistically sound, or if it's just that we happened to catch a few of them. It's a pretty small sample at that point, and they weren't misaligned. So this is showing the first 10 of the measurements that we got as part of the survey. We now have over 25, I think, that are published, and some more that are along the way. So we've had quite a few really great results come out of this, and many of these have been led by students. So the ones with asterisks have been led by either graduate or undergraduate students in our group. Many of these are warm Jupiters, but some of them are not. So I wanted to mention some of these are very nice and aligned. Some of them are not. So you can see there are these kind of non-symmetric signals that pop up as well. So there's sort of a range of planets that we're looking at, but sort of the motivation of this search or of this survey has been to look at planetary systems where you don't expect tides to have had a really important effect over the lifetime of the system. They probably could not have tidally realigned your system. And so if you're seeing an aligned system, it probably was aligned. If you're seeing a misaligned system, then it also wouldn't have had time to realign. So it's maybe expected that it would remain misaligned. So I'll highlight just a couple of the kind of science results that have come out of this survey that I'm kind of most excited and or puzzled by. Where the first is that this thing that I noticed as a graduate student seems to really hold up really nicely, where we were seeing that warm Jupiters tend to be aligned. So that's these pink points that are at the bottom here. And you can see there are a couple of yellow ones that are just ones from our survey that we added at this stage in 2022. And this is just looking at single star systems. So there are extra dynamical considerations if you have a binary companion to your system. So we sort of remove those just to kind of look at the simplest case. And you can see that even if you don't have a binary companion, you've still got a lot of really spin orbit misaligned hot Jupiters that are at these short orbital separations. But when you look at the warm Jupiters, they're all kind of lower down in the figure in these aligned orbits. So at this point in 2022, we showed that this is significant to 3 to 4 sigma, depending on how exactly you slice and dice your sample. So you can account for host star biases or just consider the full populations. But then as we continue to get more of these observations, we continue to notice some increasingly puzzling and interesting things about this, which is that even if you consider warm Jupiters on really, really eccentric orbits, like 0.4, 0.6, 0.8, they're still all spin orbit aligned. There have been none in single star systems that have been found to have misalignments, despite these really, really high eccentricities. So that's something that's interesting that has been kind of emerging from quite a few groups that are shown here, as well as ours. And we also found that if you just keep building the sample, because we just really wanted to convince ourselves there aren't biases in our sample that could be producing this lack of any misalignments at all. So we got this slew of additional measurements that were primarily around kind of hotter stars, and ended up showing that if you consider also sort of these differences at the Kraft break. So we needed to have enough systems that are around hot stars to be able to show that this was significant. Even if you sort of divide it into looking at just hot stars with hot Jupiters, hot stars with warm Jupiters, and dividing by stellar type, we still are seeing no misaligned warm Jupiters. So this really, to me, is pointing again toward this high E migration mechanism for hot Jupiters, because if you had a bunch of tilted disks, then you would expect that your warm Jupiters should be misaligned just as often as your hot Jupiters, if that's how you're tilting your hot Jupiters, because your disks should form hot Jupiters and warm Jupiters probably at somewhat similar rates. There's no reason that you'd have all of your tilted disks form hot Jupiters and all your aligned disks form warm Jupiters. It's a bit easier to invoke sort of something that is bringing your hot Jupiters in on top of that underlying population to produce those misalignments that we're seeing. One other point that I wanted to mention along these lines that kind of provides maybe additional reason to believe that your disks are the ones that are aligned and something's happening after to produce some of these misalignments is if you look at just the near resonant systems, which are the ones that are probably closer to pristine. That is, you might expect your systems to form in these resonant chains that in some cases break, but in some cases you're able to maintain something within or near resonance after the disk has dispersed. If you just look at those systems, we also see not a very large range of these spin orbit misalignments. So this is kind of the most misaligned, at least in the mean value that we found to date, and it's still only misaligned by about 20 degrees. So for these systems, we also don't see any large misalignments, which maybe lends additional kind of credence to this idea that your disks are not going to get very large tilts. You might get some range of tilts, and perhaps we could probe that a bit better by getting more of these observations in systems. We expect probably some range of disk tilts because the solar system is a little bit tilted. But we're not seeing anything like the crazy sideways, backwards hot Jupiter orbits when we look at these systems. So again, this is really pointing towards this high E migration framework for hot Jupiter formation and more generally for these tilted planets formation rather than this tilted disk framework. So two last things that I want to mention for this section. We also started looking at this in kind of different spaces to try to understand what is actually the physical meaningful factor that is determining whether you get spin-orbit misalignment. So this is a relatively new paper by Jace Resnack, a postdoc student at Indiana University. And we showed that if you actually just plot this in planet-to-star mass ratio space, you find that the highest mass ratio systems are generally pretty aligned. Turns out XO3 actually has a stellar companion, and so that sort of gets taken out of the sample, and then this one within 1 sigma is pretty close to alignment also. So all of these are pretty well aligned down here, and it seems that it's really just the lowest mass ratio systems that actually end up having these larger orbital inclinations that emerge. So this is kind of a visual of perhaps you end up with the very, very high mass ratio systems are primordially aligned. They're the most massive body in the system, so nothing can sort of excite them to larger, higher inclinations if they form in this nice aligned disk. Lower in mass, there could be other companions or something that could have induced these larger mutual inclinations. And then there's this middle region where perhaps tides of some flavor could have actually been realigning your cool star systems, but not your hot star systems. So this is one other way that you can kind of think about what regimes each of these planets fall into. And then one last thing I want to mention is that we've gotten one of these measurements for trying to understand the brown dwarf desert and sort of looking at the spin orbit measurements for brown dwarfs. Since this observation, there have been 3 or 4 more observations that have come out from other groups to try to understand this distribution for brown dwarf systems as well. I'd say right now it's pretty early days for that, but I'm optimistic that a lot of cool results are going to be coming from here to try to figure out what it is that's actually producing these transiting brown dwarfs that are on very close in orbits as well. So right now it's a bit hard to parse because, again, many of these systems could have tidally realigned, they could have been primordially aligned. It's hard to say. But as we get more of these observations, we might be able to start piecing together the picture for how the close-in brown dwarfs are forming and getting to their current orbits as well. Okay, so that was section 1. I'd like to go to section 2, which is looking at stellar companions. And this is sort of something that I got into from something in section 1. So this is actually a figure that I showed earlier in this broad array of these spin orbit measurements that we got, which is a measurement of this one system that's a warm Jupiter, Qatar 6 ABB, or rather, it's only around one of the stars. So maybe it should be Qatar 6 AB. And it's an aligned warm Jupiter that is pretty precisely spin orbit aligned, but it happened to have a stellar companion. So I said, okay, we'll figure out how that star is oriented relative to the rest of the system, just do our due diligence to figure out what we know about how the system's oriented as a whole. And if you look at the way that the host star or the companion star is oriented relative to the primary, it's moving in exactly the opposite direction of the primary, such that if you put this into any sort of orbit fitting code, it is consistent with only perfectly edge-on orbits, basically. So that's pretty interesting because all of our spin orbit measurements are obtained for transiting exoplanets. So we know that our planet is on a perfectly edge-on orbit, and our stellar binary is also on a perfectly edge-on orbit, and the system is spin orbit aligned. So this is the first binary star system that I looked at as part of the survey, and I thought, that is so weird. Why is everything so perfectly collinear that we've measured? And is it a coincidence that the first system that I looked at happens to have this beautiful sort of exactly coplanar configuration? So around the same time as this, there were a couple of results from two different groups, one looking at TOI systems, test objects of interest, and another looking at KOI, Kepler object of interest systems, that showed that if you look at transiting exoplanet systems that have wide binary companions, or sort of moderate to wide binary companions out to a couple hundred AU, then you end up finding preferentially that your binary orbits are edge-on more often than you would expect from just random orientation. So there's this peak at edge-on inclinations that you can see here that deviates from just random isotropy for your binaries relative to your transiting exoplanets. So what this is saying is effectively that instead of having just random binary orientations, you tend towards seeing something like this, where at these sufficiently close orbital separations, so within about 700 to 800 AU, you end up seeing that your planetary systems kind of line up nicely with each other. So I was curious about what this meant in terms of adding this extra layer of the spin orbit orientations together with the ways that your binaries were oriented. There are a lot of angles in such a system. We'll just focus specifically on, again, the spin orbit angle we've been talking about throughout this talk so far, as well as this orbit-orbit angle. That's, again, a sky projection of the position between your two stars and the relative velocity of one versus another. And this is just showing a couple of examples of what that could look like, but you can have all kinds of configurations that are in between as well. So this top one is basically what Qatar 6 looked like, the really weirdly collinear one. So just taking all the systems that had spin orbit measurements, cross-matching with Gaia, figuring out which ones had bound stellar companions, we ended up finding 9 out of the 40 systems that we looked at showed this beautiful collinearity where they were within relatively small error bars, they were basically consistent with perfect alignment across both these axes, both the spin orbit orientation and the orbit orbit orientation. And this is more so than you would expect from isotropy. So you do actually expect a peak towards edge-on for isotropic orbits just because of the viewing geometry. But we ended up finding that this is actually even stronger than you'd expect there. So this is just a visual of what that looks like, but then just showing this is a wrapped Gaussian on a circle, since we're looking at kind of polar coordinates here. If you had an isotropic distribution, then you would expect your distribution to look like this, where you sort of have a range away from 90 in addition to this peak at 90. And we see a much larger peak at 90 degrees that corresponds to lots of these systems being very, very close to alignment, specifically when we're looking at our cool stellar hosts. But we ended up actually seeing, if you take out your hotter stellar hosts, and I was interested in difference of the Kraft break because I was looking at spin orbit orientations, and we know that there's a difference there. So wanted to see if it also showed any distinction in the orbit-orbit distributions. We end up not seeing this trend towards alignment for the hot star sample, but instead we end up seeing this sort of distribution that to me looks a bit more like the outcomes of Kozai-Leadov oscillations. So you end up with sort of a peak around 140 degrees and around 40 degrees, and 90 degrees again is edge-on, like what we have for our transiting exoplanets. And if you invoke von Zeipel-Leadov-Kozai oscillations, you also end up with, for the quadrupole distribution of mutual inclinations that you get for those systems, you also have this sort of double peak at 40 and 140. So this is just a mechanism where you trade off inclination and eccentricity for hierarchical 3-body systems. So all the systems that we're looking at here are such systems that are kind of central star, binary star companion, and a planet that's around your central star. So many of them, if you have sufficiently large initial mutual inclinations, are going to be prone to this Kozai mechanism. So that's probably, we think, what's happening for at least some fraction of the hotter star systems. But then what's going on with this weird peak where everything's kind of coplanar? So there, probably what is happening is this dissipative precession in your circumstellar disk. So if you have a disk that is being perturbed by a stellar companion, then your disk is going to precess about the normal plane to your stellar binary. And as it is precessing, it's going to be resisting warping, and it will dissipate energy and get closer and closer to your binary plane, such that you ultimately end up producing a planetary system that is closer to this alignment. So it turns out that actually your binary companions can sort of push your systems closer and closer to alignment. They're not necessarily always going to be wrecking balls that destroy life through cosi. They can actually sort of push them closer to this aligned state where they will never be able to undergo cosi. And so this is something that's a strong function of quite a few of your disk parameters. And so Konstantin Gerbig, a fifth-year PhD student at Yale, modeled what this process would look like and showed that as a function of sort of semi-major axis of your stellar binary, what the efficiency would look like. This is actually probably an underestimate of the efficiency because he assumed circular orbits for your stellar binaries. So many of our binaries are going to be on eccentric orbits. So this dissipative precession is probably a bit more efficient than would be suggested by the figures that are shown here. And I think probably one of the more exciting results from this paper was that we showed that if you look at the mass ratios of the systems where you see something closer to alignment versus this just random isotropy, if you have a companion star that's much more massive than your primary, then this precession mechanism is going to be more efficient than if your primary star is being perturbed by a very low mass secondary. So you would expect to have a stronger trend towards this alignment if you have a massive secondary. So that's this on the right is near equal mass, or your secondary star is more massive than the one with the planet around it. Whereas here, we're looking at systems where your secondary star is lower mass, and we see that those are closer to consistent with isotropy. So we're pretty sure that this mechanism is playing a pretty important role in shaping many of these systems where we are seeing this nice alignment, and we are seeing this sort of trend towards it's pushing towards this final stage of your systems will want to, if they reach the final end stage, they'll want to be kind of close to this perfect edge-on orbit-orbit alignment that we see in many of these systems. So probably both of these mechanisms are playing a role for binaries. They are not fully inconsistent with each other. You can have some of this happen on the right, but if you don't reach a low enough mutual inclination in the end, then you can still have cosi happen afterward. But you can also get to just a low enough inclination that you never get cosi in the first place. So taking this and just thinking about what the implications are, I got really interested in this idea that, okay, well, if your orbits are nicely aligned, then that means that if you just take a look and find all of the edge-on binary systems in the local solar neighborhood, those would actually be really great planet search targets, because those are the systems where you might actually expect your planetary system to also be edge-on. And that means your transit probability is higher, sure, but you still probably have a relatively low likelihood of transit, but also your radial velocity semi-amplitude is bigger. And so you end up with this boost in your signals that you'd expect. So Joseph Hand, who was an undergraduate at University of Kansas, who worked with me last summer as a Hoplite scholar at Yale, mapped out just all of the systems that are relatively bright. So G is less than 14 in Gaia magnitude for both of your stars that are on these very nicely edge-on orbits. We kind of require that they have to be pretty precisely edge-on. So this is the uncertainty and the inclination that he pulled out from just putting these through the lofty Gaia orbit modeling process. And so most of them are within a couple of degrees of uncertainty, are consistent with perfect alignment. They're perfectly edge-on. And many of them are these FGK stars. And so these are kind of our classic planet search stars that we expect are probably some of the better targets that you can actually search for planets around. There is the caveat that some of them are in relatively close binaries. So this is angular separation, 1 arcsecond and 2 arcseconds. And so you'd have to be able to resolve your 2 stars separately. But there are also quite a few that are actually fairly wide. We show this 200 AU line where maybe you expect planets to be suppressed below there. So they might not be the best targets to search, but there's still a good space where you might be able to find some cool planets and actually maybe compare your planets across the two stars within your system, which is this idea that has been kind of haunting me. I just think it would be so cool to actually compare your two stars in the planetary systems around them, binary systems. So we also just quantified, what is the boost in likelihood of actually getting a transit. So assuming either perfect alignment versus 20 degrees dispersion of the alignment. So you might not get to that end state for every single system, as well as what's the boost in your RV semi-amplitude, which is generally a factor of something like 1.6. So it might help if you're looking for really tiny planets to search for systems where you think that the system, there's reason to believe that it might actually be edge on. Okay, so one last thing I want to mention about the binaries is this WASP-94 system that I've been super fascinated by, and that kind of also was part of what fed into this previous project that I talked about. And this is this crazy system that no one ever seems to talk about for some reason, but it has 2 hot Jupiters in it. And hot Jupiters are very rare. We see them around only about 1% of stars. And this is a binary star system that has a hot Jupiter around the primary that's transiting, and another hot Jupiter around the secondary. They're very similar stellar types. And the 2 stars are about 2,300 AU apart. So it's kind of strange that you would have 2 hot Jupiters within the same system. But there may be a lot of different ways that you could form this. And so a fun kind of side project that I've been working on with an undergraduate student who's really outstanding was looking at this idea of whether you can get double hot Jupiters through mirrored Kozai evolution. So the idea here is that I mentioned this Kozai leadoff mechanism. And if you have a planet around both of your stars, so if you start with a cold Jupiter around each of your stars and you just evolved them in a mirrored fashion, then you could very naturally produce hot Jupiters around both stars through this Kozai lead-up evolution. So what Nina did was just sort of consider, this is sort of just assuming that your binaries are randomly distributed for hot Jupiters, which we showed is probably not exactly the case, but we don't know exactly what the distribution of mutual inclinations is, so we just took kind of random orientations. And she found that up to about 9% of your closer binaries, if you assume pretty optimistic eccentricities that give you good or relatively short Kozai lead-of timescales, then you could actually form double hot Jupiters in quite a few of these systems that have a single hot Jupiter in them. So that's something that I've also been really fascinated by, is this idea of maybe we should search around the secondary stars for some of these second hot Jupiters that could exist in these binary systems, since we know of quite a few hot Jupiters that are in binaries, and many of them are in sort of twin binaries where your 2 stars are kind of similar types. Okay, so this is my conclusion slide, but I think I might have time to do my bonus section. So I think I might do my bonus section. That's okay. Do I have time? Okay. Awesome. So the last thing that I wanted to talk about in my bonus section is the test mission. So this is another line of work that I've started on a few years ago, kind of slowed down on, and I'm starting to pick back up again now, looking at how the test mission can be used to study the distant solar system. So there are a couple of branches to this. I would say the way that I initially got into this was kind of the first thing that I'll talk about here, but I wanted to start with what exactly is the test mission. So this is a survey that has 4 very large cameras. The pixels are pretty large. They're about 21 arc seconds apart, but it's looking at 21 arc seconds across in size. But TESS is looking at this huge swath of the sky. This is showing the initial primary mission, where it kind of scanned around, it stared at each region for 27 days at a time. So you have continuous photometry for all the sources in those fields for about a month. And in this primary mission, this gap in the middle was where the solar system lies. so that's exactly where TESS didn't look in its initial mission. But since then, it's actually filled in that gap, and it's sort of flipped its cameras around, and it's looked at more than 95% of the sky at this point. I believe it just has some small gaps that remain where they haven't gotten this full month of observations. And TESS has now been operational for, I think, since 2018, so 7 years now. And it has continually been observing. And so many of these regions have been revisited, and you have multiple month-long observations for much of the sky at this point. So I got interested in TESS specifically as a way to possibly search for Planet 9. So there's this idea that has been kind of around for a little while now, that it was first, I would say, pointed out by Trujillo and Shepard in 2014, that there is this observed apsidal confinement of your very, very distant extreme trans-Neptunian objects in the very outer solar system. So the idea here is if you take just your objects that have semi-major axes greater than 250 AU, so these are really, really wide orbits, the entire orbit is outside of Neptune's orbit for all of these bodies. You're biased, first of all, towards the very, very high eccentricity orbits, since you can only see them at their periastron approach. But if you take just the ones that are on these long-term stable orbits, that is, they're not getting significantly perturbed by Neptune over long integrations of the solar system, they appear to be potentially clustered on one side of the sky. And this is something that you would not expect because none of the orbits in the solar system close perfectly. We are not in a nice two-body system. And in particular, you get this extra perturbation from here, j equals 5 through 8 is the 5th through 8th planet in the solar system, the most important perturbers, the massive giant planets that are in the outer solar system. And so because of this, you'd expect your perihelia, this omega that defines which way your orbits are pointed, to sort of change over a time scale such that you'd spread out your orbits over about 1 billion years. I should mention that whether or not this is statistically significant has been pretty hotly debated in the literature. There's been a lot of back and forth on this. But if this was true, then this could be indicative that maybe there's something missing in our picture of the outer solar system. So there was this idea put forward. There have been a couple of iterations of what this would look like. But if you zoom way, way out in the solar system, kind of the most up-to-date expectation for what Planet 9 would look like is this 6-ish Earth mass body that would be on a semi-major axis of about 380 AU, somewhat inclined orbit, and a somewhat eccentric orbit as well. So this is kind of the most recent Brown and Batygin version of Planet 9, if it was there. And if that Planet 9 existed, it would actually fall directly, it's like right here in terms of where an undiscovered planet could actually be. So it turns out you actually could hide planets in the outer solar system. There's this whole range of space where we wouldn't have completeness in terms of our sensitivity, where a planet could be hiding anywhere that hasn't had an all-sky survey that would rule it out. So if it's sufficiently small or low mass or low albedo also to be seen. There's, the definition of a planet is sort of our lower limit here, where it's going to be a dwarf planet below a certain limit. There is a limit sort of in terms of your semi-major axis, where you would see perturbations on other solar system bodies if your planet was too close by. So in particular, we have very precise ephemeris measurements from Cassini that would have been able to rule out a planet that was too close to us. Or if it's too far away, then it probably would have been unstable in the sun's birth cluster, and you wouldn't have kept the planet over these timescales. So if you had a Planet 9, it would fall in there. You could also be hiding other planets within this space. And so we said, okay, well, TESS is searching the entire sky. It's just got tons and tons of data. So let's see if we're able to just see what can come out of the distant solar system if you search with the TESS data set to go to the faintest limiting magnitudes that you can with it. So a few years ago, I built this pipeline to basically search for very faint, slow-moving outer solar system objects. This is a shift and stack pipeline, which is saying you have a month of data and you shift it and add it together along the path of an object to get just a single point detection that would correspond to possibly a real object, hopefully a real object. And we consider only, and you do get false positives for this, so that's why I say hopefully. And we consider only linear paths. So it actually turns out that this method is much easier to do for very distant solar system objects than closer ones, because you can ignore the motion of the object itself. You're just looking at the Earth moving past the object. And so you just get these linear paths for solar system objects in the very, very distant solar system. So we made this pipeline. This is just showing a proof of concept of a recovery of Sedna, which is a distant extreme trans-Neptunian object. So on the left, we're seeing basically just a video of a region of the TESS images where we're seeing asteroids moving through. There are these kind of blank spaces where there are stars that we masked out. And then on the right, Sedna is popping up. You can't see it in any individual frame here, but we're just shifting and adding together those frames as they pop up on the left to add up to produce this much more significant signal on the right. Okay, so Sedna's, V equals 21 or so at this point when we were observing it. And so we showed that you can pull it out if you know exactly where it is. But more importantly, we also showed that you can pull it out if you didn't know where it was in the first place. So on the left here is shift and stack recoveries of a few known objects along their known orbital paths, or along, these are all linear shift stacks, so along the paths of where we know the objects actually are. And then in the middle and right, these are two different iterations of this pipeline that did a blind search. So they said, okay, we're going to try every single possible path for an object between 30 and 800 AU that it could feasibly have, and just consider linear paths that are just the Earth's parallactic motion again. And you recover Sedna really, really nicely. We also recover BP 519, which is a somewhat fainter object, equals 21.81 at the time of observation, through this blind search. And we don't recover the faintest object we looked for, but this is probably both an indicator of the test's limiting magnitude, as well as the fact that this is the most nearby of these objects. So it actually has a bit of a curved motion because of its orbit actually contributing to the path. And we don't consider that at all within this framework. We're only considering linear paths, which should be totally fine for Planet 9, totally fine for very, very distant objects, but doesn't work so well within 40 AU or so. So Ben Casses, a graduate student at Columbia who I've been co-advising, has been building just a more general pipeline to process new test sectors and just immediately put out what some of these shift stacking candidates are. It's general, so it would be looking for just anything in the outer solar system that hasn't been found before, and showing kind of what you would need to do to follow them up. But ideally, we would be able to use returns to the same point. So Tessa's looked at the same parts of the sky multiple times and actually linked together those paths. So that's sort of the goal of what we're working toward with this framework, to do sort of self-confirmation with Tess. So this is just kind of an outline of what that pipeline is looking like. And it's pretty much in place, and we're sort of just tweaking primarily the neural network component at this point to decide exactly what thresholds we want to use for pulling out candidates that we actually believe and say are probably realistic ones. So this is just showing a video of one of these candidates that we pulled out that was Tessa's first TNO detection. So this was a nice sanity check where we went on Sky and used DECCam to show that one of our candidates that we pulled out was actually real. And so you can see it kind of moving through here. So this is kind of ongoing. I wanted to mention that Tess happens to look over the same parts of the sky that Batygin and Brown suggest is where Planet 9 is most likely, which is, of course, where the ecliptic plane and the galactic plane meet. So that's unfortunate, but that is where I would hide if I was Planet 9, so I get it. And Tess actually looks right at those spots as well. And so this is kind of our target sectors, is just looking at these cameras that are really directly over this red spot that's highest likelihood. One last thing that I want to mention is, while you're looking at cool stuff with Tess, you find other stuff accidentally. So we accidentally found Uranus and Neptune while we were doing this search. And it turns out that we actually have quite a lot of continuous photometry from Tess of Uranus, 77 days of consecutive photometry, as well as 50 days of Neptune photometry that's spread out. So it's about 25 days 1 year, and then 2 years later, another 25 days. So Kenny, a second year undergrad who's also totally outstanding working with me, has been actually just pulling out what those light curves look like, and pulling out some of the periodicities from that light curve, or from each of these light curves. We've been focusing on Neptune to start, but are also planning to apply this to Uranus, and has been mapping these onto wind speed models from Shramovsky et al. 1993 to figure out if these correspond to cloud features, exactly where on the surface of, in this case, Neptune, those clouds would lie. So this has been just a fun, we accidentally had this data set and just wanted to see what we could do with it and what we could find from it. And so it looks like there's some candidate features that we are starting to pull out. And we can cross-match these with some Keck images that were taken around the same time, or actually at the same time at certain points within the test photometry. And so this has been a nice sanity check to actually show, okay, well, if you integrate over all of this disk, then this is the light curve that comes out of it, and you can actually see a couple of snapshots of what the non-integrated flux of Neptune looks like there too. All right, so this is my actual conclusion slide that has the bonus in it as well. So I have, in addition to conclusions, a whole bunch of open questions because I think that there's a lot more to be done along each of these research directions. And so I'm excited to see what comes in the coming years and to take any questions and get any thoughts from you. So thanks, everyone.
Thank you very much, Malena, for these very interesting results. So do we have any questions? First, yes, so please go ahead.
I was wondering, with Gaia, the next release, so getting the astrometric orbits, might be able to say about binaries and the alignment of more distant period planets. Are you expecting them to be more like the warm Jupiters and aligned?
So are you saying planets that would be discovered with Gaia, or?
Yeah, the long period giant planets, Gaia.
Yeah, I don't know that I have a strong expectation for that, but I think it depends on how you actually form those planets, because the ones that have been found so far are these super Jupiters, I think on fairly eccentric orbits, and I'm not totally convinced that those would have had to form within the disk. So maybe there was some kind of impact stage or something that would have produced them that might mean that you wouldn't expect them to be spin orbit aligned. But we also don't actually really know what the alignment of the outer disk is, because everything that we're probing here is for transiting exoplanets, and we've seen like disk shadows from broken disks as well. So I don't have a super strong prior on exactly what we'd expect for such wide orbiting planets. And I think it depends on how they formed. So it might be this feedback cycle where you might be able to actually inform that, and whether you often have these broken disks as well.
Other questions for the speaker? Yes, Ty?
For the TESS Planet 9 work, is there room there for a citizen science approach to looking at the results that come out of the pipeline? Have you considered that?
There might be. So we are attempting to use a neural network, which I suppose you could actually just have people do rather than using the network. And in the 2020 paper, we had actually been looking for some Planet 9 candidates, and we didn't find any that looked like they would be Planet 9. We found candidates that would not be Planet 9, that would just be outer solar system objects. And those came out from me going through a lot of images manually. And so that actually could be nice to have help broadly from citizen science to do something like that. And that would be necessary to do something like that at scale. But I'm hoping that the neural network can vet down to some degree, but you probably will be tossing certain things as well using a neural network, where if anything looks slightly out of the ordinary, it'll just be thrown. So yeah, so that's a good point. There maybe that could be added into the Backyard Worlds Planet 9 project in some way.
Okay, other questions? Yes, Fuda, go ahead.
In the process of migrations and perturbation, do you precession as well, and whether that could be detected?
Which planets are you referring to? The hot Jupiters?
The misaligned hot Jupiters.
Yeah, so a lot of them are on close in enough orbits, and if they're eccentric, then you may be able to see apsidal precession. There have been some studies of a couple of specific hot Jupiters that are most promising to find this for. And in particular, WASP-12b comes to mind as a hot Jupiter where their continuous monitoring has been attempting to check whether the change in its orbit is either apsidal precession or like tidal in spiral, and if it's falling into its host star. And it looks like it's actually falling into its host star. But in theory, if it was precession rather than falling into its host star, then you should have been able to see that for that system. So there are a couple of them where the timescales are short enough that you'd actually see the precession, but it's not a lot of them. And many of our hot Jupiters are on circular orbits, so the precession would not give you useful information. I don't even know if it makes sense to describe precession for circular orbits. So.
Yeah, Mark.
Laughlin and Fortney and I have a paper where we tried to make reasonable guesses for albedo and magnitude of the. How close are we to being able to start testing those kind of guesses for a mass radius relationship for a icy body and 6 Earth masses and so on?
Do you mean in terms of what we haven't found with
some
limits
you've got?
Yeah, so I think you'd be able to map out from what hasn't been seen a magnitude limit, which you could then map into albedo. So this is kind of similar to what's been ruled out by WISE as well, and you could do that with TESS. So I would say after doing a full search with TESS, you probably could actually say it cannot be above some limiting magnitude, with the caveat of if it was directly next to a really bright star or something, then you wouldn't have seen it. But you could put some magnitude limit that you could then translate into albedo, and that should be feasible with existing data. Just is a matter of running the code and actually doing all the injection recovery tests as well.
I want to make sure we don't have any. Is there any question online? Okay, it seems not. Any other questions here? Okay, then if not, let's thank our speaker again.